All right, still on rock deformation, let's take a look at Enema Falls. Enema Falls is a form of deformation in rocks in which one half of the rock mass or a section of rock has collapsed or moved downwards relative to its other half in such a way that both halves are separated along a plane of stress or weakness. Typically, we find Enema Falls more in areas of crustal stretching or shaking. That is in areas where you've had more of extensional plate movement. And typically in those areas, because the plates are moving away from each other, it creates a space, and the creation of space leads to the sagging or the collapse of a block of rocks in the middle of the plates that are moving away from each other. A few hints on how to identify Enema Falls. First of all, strata discontinuity. So if you have a number of layers, such that you can actually trace one from one end to the other originally, but if at the present time you see that they are consistently discontinuous, especially along a vertical to sub-vertical trend, maybe the interpretation will be that you already have a normal fault in this area, and that's especially if one block seems to have moved down relative to the other, and then you can infer that potentially you've had you have a normal fault movement in that area. Another thing that will help will be vegetation. So supposing standing on this area, for example, I have a different kind of vegetation. Let's say consistently I have one kind of vegetation naturally in this area A, but in the eastern area B I have a different kind of vegetation, let's say more of grasses in the natural sense. So the question will be, although this is what I think I'm looking at, the question will be, why are they the vegetation types different in both blocks even though they seem similar? Now the difference in vegetation can actually be a hint that the mineralogy in this location A and B are different, and if the mineralogy or the nature of the underlying rock is different, then maybe they are different rocks. So we have to now think in 3D sense, and this could be what we're looking at. So what was originally a puzzle as to what are we looking at here, with the 3D sense of it, we're able to figure out that truly the rock type here in this western area and one in the eastern area are different, because we see that we have juxtaposition of different genetic kind of rock, and that might actually be the reason why we have different types of vegetation on both sides, on both halves on the surface. So what I'm saying is, in general, an understanding of the distribution of vegetation in any particular outcrop, especially if you're standing on a flat surface, can give you a hint if you have an underlying fault plane that you really cannot see. One other element again will be rock facies contrast. So supposing let's say I have this facies A in this area, and then moving to the west, abruptly I see a different facies B. It tells me something might have caused that abrupt change, and in most cases, especially if you're able to establish a sense of movement such that these layers in facies A, you actually find them up and shallower in the other area in the west, then we're able to make a case that maybe we have a fault separating the western and the eastern block. So one other key thing you can also look out for is differences in dip pane. So supposing I have a bunch of strata dipping in this direction, and then I have another band, another set of same strata and same order dipping in a slightly different angle, and then I also have yet a third arrangement. Now the first question will be what has moved up and what has moved down. So what is very obvious here is that we have different dip panes. We have this dip pane we have another one which is more like horizontal, and then we have this other dipping such that the strata are dipping in the opposite direction. The first thing is, if I establish that this is sequence and in this other area is this way in the middle block, perhaps I have a fault here, and then in this other area it tells me also that I probably have a fault in that direction. So I'm able to establish the sense of movement just by looking at first of all the differences in the dipping and also the elevation of the individual or rather the bulk stratigraphic units from one block to the other. So these are surface outcrop examples of normal faults, pretty much very well shown here, and then this is the interpretation. So we see very clearly that this block has moved down, or kind of sagged relative to this block along this plane of weakness. Okay, this is yet another example where we see clearly the hanging, what we call the hanging wall, is moved down relative to the footwall, which sits underneath the false plane. We have this area that potentially, pretty shows some element of plastic movement, which might be as a result of fault drag, or maybe the rock nature here is different. That's behind the fault. It might be more, more of rocks that are less brittle, and they take this, curved shape, which is typical of, or which might be as a result of a plastic deformation in that area. So this is another example, bunch of normal faults. If we take, for example, a particular layer, you can actually see consistently that each time you're going across a plane of discontinuity, the layer to the eastern part of it seems to have moved down, and with that you can actually put a number of faults here, normal faults. And this is just one very good example of an area where in extensional domain the rocks have kind of gone through a bunch of deformation, but in this case extension or stretching has caused sagging of different parts of this or different sections of this rock. This is the cleaned up interpretation of that outcrop. Yeah, so thank you very much for your time. This is all I have to share. Do let me know if you have questions, and do not hesitate to follow us on our social media.